File IO, which is actually a shorter module. It's not as, because it's pretty simple. You'll find that even at the end of today, you'll see that basically you know how to do this already, especially File IO. You know how to print to the standard output. Well, guess what the standard output is? It's a file. What's the standard input? It's a file, right? In fact, you'll find out that everything in a Unix-based system is a file, right? Now, usually when we say file, we're referring to a piece of memory that's stored generally on disk, right? A text file or your source file or something like that. But what about directories? Directories are actually files in a Unix-based system. Programs are files. Files are files. Buffers are files. Sockets, the thing that you open up to communicate to another computer over a network, that's a file. To communicate to a computer from computer A to computer B, what you do is you open up this thing called a socket. A socket is nothing more than a file. So that when one computer writes to that file, right, that's being sent over the network, the other computer reads from that file. And that's how networking works. A socket is nothing more than a file. So all these things, processing of data, writing it to a file, etc., these are used in multiple different instances. And you've been using them all up till this point by reading from the standard input, by writing to the standard output. And that's when we say read, that's what we mean by file input. When we say write to a file, then we're outputting to a file. Files can be either binary, right, pure data, or plain text. What we're going to do is we're going to restrict most of our attention to plain text files, right? Now, these files are not necessarily for human consumption. We've seen things like CSV files, XML files, JSON files. Those are files that hold data in a plain text manner, so it's just a text file, but in a structured manner, right? It's not necessarily meant for a human to be reading XML files. If you are wanting to process binary data files, then bring in a library to do so. That's what we did with respect to photos, or the images that you processed. Anytime that you put them through a filter or you reverse them or something like that, we gave you a library to handle the binary data. Right? If you're ever dealing with binary data, audio files, video files, or something like that, don't worry about the low-level details. Just bring in a library to deal with that kind of stuff for you. All right? Again, even plain text files might be structured. You could even have, say, base 64 encoding. That's how email works. So if I take an image and I want to send it to a friend via email, that image is not sent in a binary format. Email is completely 100% text-based. So what happens is that digital file is then encoded in base 64 format. So for example, if I just had the message, hello world, how are you, and I encode it, it looks something like this, right? It doesn't look like the original text, but it is using text to represent that data. Lowercase a through z, uppercase a through z, and the numbers 0 through 9 give me, 62 characters? Plus, I forget what they are, what the other two characters are, but basically it gives you 64 possible characters here to work with. It's a way of taking binary data, which is just a bunch of bits and bytes, right, and converting it to text data so that you can send it over the network as text data. Okay. Again, we're not going to deal with that directly. Instead, if you ever need to deal with binary data, bring in a library to do it for you. Right? All this stuff, it goes to EDI, which is electronic data interchange. These are common operations on data that you need to get it from one computer to another computer, and they may not necessarily even be speaking the same language. It could be completely different operating systems, completely different languages, completely different technology stacks. But one computer can still talk to another computer by using this data interchange format. Say CSV, XML, JSON, or some base 64 encoding. Okay? We're going to keep it simple. We're going to keep our attention to just plain old text files. And the basic steps to working with those files are going to be to open up the file, process the file, and then make sure that you close the file. Right? The first step and the last step are super easy, so that's what we'll start with here. Right? How do you open up a file? Opening up a file can be done using a function called open. Right? So in C, you can open a file using the function called fopen. And what do you think it stands for? File open, right? It takes two arguments. Right? The first argument is the path/file name of the file you want to open as a string. Right? And the second one is a string representing the mode you want to open it in. And now we're going to restrict our attention to just two modes. It could be either W, right? Lowercase w, meaning this is you're going to write to the file. Right? This is file output. Right? Or you can have R, which is read from a file. This is file input. Okay? One of those two modes. Now, there are other modes. There's like append mode. There's binary mode. There's a couple of others, append and read and write mode. Various combinations that you can come up with. Again, we're going to keep it simple. We're going to keep with reading and writing from a plain text file. Right? It returns a file handle or pointer, which in C is represented as all uppercase FILE star, which tells you that it's a pointer. The way that it works is when you open the file, the pointer will be pointing to the first character on the first line of the file. As you read through the file, either line by line, or character by character, we'll look at both ways, that pointer advances. If you read a character, then it'll advance to the next character in the file. If you read another character, it'll automatically advance to the next character. If you read an entire line, it'll go to the next line, right? So that's why it's represented as a pointer here, because it is literally pointing to one of the pieces of data in the file. Right? Let's go ahead and take a look at an example here. Oh, by the way, right? It returns a file pointer. What happens, do you think, if it fails? If the opening fails for any reason, it returns what? What's the only thing that it can return to indicate that something went wrong if it's returning a pointer? Null, right? It returns null. What could go wrong? Let's find out. So let's go ahead and try to open up a file called myfile.txt. So file f is equal to fopen myfile.txt. And I want to open it up for reading. Okay? Now look over to the side here. I've removed everything except for the demo file that we're working on right here. Do you see a file named myfile.txt? Nope. Can I open up a file to read it if it doesn't exist? Nope. Consequently, it will fail. Right? So if it's equal to null, that means it failed. Let's go ahead and print out a message. Printf cannot open file. End the line. There we go. And I will show you that this will fail. And let's just make sure that in the event that it does succeed, file opened successfully. There we go. Right. So which one will happen here? Well, the file doesn't exist. So obviously you can't open it up to read it. And you cannot open that file. So if it fails, then it'll just return null, and you can check for that. Let's open up a different file in a different directory. What if I went, I don't know, up one directory? Actually, I'll just go all the way over to etc passwd. Do you remember that file? We briefly talked about that. What does it look like? More etc passwd. There we go. It's the password file. But thankfully, we don't have passwords in it, right? They've been redacted. All these X's right here. It's a colon-separated value file, each one of these pieces of data. Now, X is where the password is stored. Of course, it's been redacted. It's been removed. So, should I be able to open this up for reading? Well, yeah, there's no problem with reading that. But should I be able to open this up for writing? Let's find out. Should I be able to change the user contents just as a regular old user? Probably not. So if I don't have permission to open up a file for reading or for writing, then you cannot open that file. So it can fail if the file doesn't exist, if the file that you're trying to open, you don't have permissions to do so, but also, let's look at another one. If I just opened this up for reading, by the way, it would be successful. Why? You can read it all you want. You just can't write to it. Successful. But where are the real passwords stored? In the etc shadow file, right? And should I be able to read that? Probably not, right? Because passwords are actually stored there. Now you can do, I'm a super user here, so I can actually look at it. We tried this in the morning class, but I don't think that the passwords are even still stored there. Or it might be passwordless, right? All those stars, those asterisks there are not actually passwords. So I'm not sure where the actual passwords are stored anywhere, right? But I was able to do that because I'm a super user do the following. That's what sudo stands for, super user do. And I can actually, you know, print it out. But over here, I shouldn't be able to see it at all. If I want to open up the Etsy shadow file for reading, it's going to fail. Oops, nope, sorry. Run it, a.out, there we go. Cannot open file. Right. So if you don't have permission to open up a file, it will fail and it'll return null. Let me open up that myfile.txt for writing. Right? Remember, if I opened it up for reading, it doesn't exist. You can't read from it. But if I open it up for writing to it, it doesn't need to exist, does it? It'll automatically create it for me, and then I can start writing to it. So let's go ahead and run this. File opened successfully. Now, I don't see the myfile.txt over here, but that's because sometimes it needs a kick in the butt and refresh. And guess what? There it is. Now, what are its contents? Nothing, because I didn't write anything to it, right? I skipped the second step of this this three-step process. Did I actually write anything to the file? No. Okay. Before we do that, though, let's talk about that third part right there, right? Closing a file. Once you are done processing a file, you need to close it, right? Failure to close it may result in undefined behavior. Right. So 99 times out of 100, the operating system will save you from yourself. It's that 1% of the time that you don't close it, the buffer is not fully flushed, or whatever, something happened, and you've got either file corruption or the file just will not exist. Right? So if we use fopen to open a file, what do you think that we use to close a file? To close a file, use fclose. Right? So let's come back over here and do that. Right? Now we haven't processed the file at all, but I can still close it. Fclose f. Right? You pass it the pointer, the file handle that was opened. Right? In this case, f. Right? Same behavior as before, but at least it was correctly closed. Okay? Just like memory. If you don't clean up memory after you're done using it, you get a memory leak. If you don't close a file after you've opened it, you could get file corruption. Right? Let's actually do something now. So let's actually do some file output because that's the easier part, right? So to do file output, you already know how to do it. To keep it simple, just use fprintf. Right? So we know what printf does, right? It prints to the standard output. What do you think that extra f in front of fprintf is? You print to a file, exactly. So let's come over here, and let me go ahead and create some variables. Int x is equal to 42, double foo is equal to, I don't know, 10.54321, and char name is equal to School of Computing. Right, there we go. Now let's go ahead and print those things out in the standard input, or the standard output, excuse me, right? So x is equal to %d. We'll end the line there. Foo is equal to %f. We'll end the line there. And name is equal to %s. End the line there. And we'll print out x, foo, and name. Now, if I just ran this, it would, of course, print to the standard output. X, foo, name. We can clean that up a little bit here by getting rid of those spaces. There we go. There. X, foo, and name. All right? But what I want to do is I want to print to a file instead. So instead of using printf, I use fprintf. Everything stays the same, except now you need to specify which file do you want to print to. In this case, I want to print to F. Right? I want to output to that file the following. Right? You can do this as many times as you want. You can do this in a loop. If you've got a whole bunch of data, you can make a whole bunch of printf statements. Right? I will go ahead and print it out like this. File opens successfully. No output to the standard output now. But if I open up my file over here, guess what? There's the contents that would have otherwise been printed out to the standard output. Okay? How many lines are there? 4, right? Why 4? Let's come back over here to demo, right? I printed 1 end-line character, 2 end-line characters, and what did I do at the end? Another end-line character. So 3 end-line characters, 1, 2, 3, giving me a 4th line, but it just so happens that that 4th line is empty. There are only 3 end-line characters. Now there would be 4 end-line characters, right? An empty line and 2 empty lines at the end. You do have to be careful when you're processing a file and you run to the end of the file and there are empty lines. What do you do in that case, right? We'll talk about that in a moment, right? But otherwise, that's file output, right? You just use take everything that you know about printf, copy paste that knowledge, and you know how to use printf now. So again, instead of printing to the standard output, it prints to a file. Everything that you know about printf, all of the placeholders, all of the formatting tricks, all of those things, they work equally well in fprintf, right? The only difference is that it takes one new argument, the first one, the file handle that you wish to print to. Okay? I'm going to make sure that you've got all of this in the notes. There you go. All right. So the other part, and this is only this slightly harder than what we've done up to now, but file input. Right? So you want to read from a file. Right? This is what file input means. Right? We're going to keep it simple. Right? You can read character by character or line by line. Right? We're only going to look at 2 ways here. We're going to look at 2 ways to keep it simple, 1, and 2, to keep it safe. There are several extremely dangerous ways that you could read from a file input, like using fscanf, like using a couple of other functions for puts, that's for file output, but there are a couple of other functions that are extremely dangerous to use because they are susceptible to a buffer overflow, where you can at best cause a segmentation fault. I want to keep it simple and just look at these 2 ways. Right? To read character by character, use fgetc. Right? Well, what do you think that stands for, first of all, before we move on? F, file, get, and C, if you're going to go character by character, C is going to be your character. File, get a character from that file. If you're going to read line by line, use fgetS. Right? So again, file, get, and in this case, S stands for an entire line. An entire line of characters is going to be a string, exactly. Right? So let's go ahead and focus on the first one, using fgetc. All right, let's see. You can use fgetc to, and it returns a single character, the next character in the file. Right? It automatically advances to the next character in the file so that you can read it over and over and over again. Right? So let's go ahead and take a look at this. I'm going to use the same file here that I just created, right? This file right here, and I'm going to start reading from it. So instead of writing to it, I'm going to read from it. Oh, by the way, before I do that, suppose that I want a different output now. Let's go ahead and say, hello world. Hello world. There. So that old data, what's going to happen to that old data? Now, before I run this, take a look at the contents of my file. Useful data. Right? I don't want to get rid of that useful data. If I get rid of that useful data, it's going to be lost. When I run this, what do you think is going to happen? It's going to put hello world into that file. What about all that other data? All gone, right? There is no undo. There is no undelete. There is no oopsies, right? If you start writing to a file, that's it, right? Whatever was in that file before is absolutely gone, and there is no recovering that file. So, for example, I'm going to cut and paste this. I'm just going to copy this. What if I opened up myself for writing? Okay. Save this. GCC. What am I about to do? I'm about to donk this file, right? So, okay, that one's still hello world. Uh-oh. What happened? All of my source code is now gone. Don't open source code files. If you do, this is why we have backups. Make sure that you are downloading them at regular intervals, okay? So I will get rid of this immediately, myfile.txt. And let's go ahead and open that up for reading. I know that it's going to work, so I'm just going to go ahead and get rid of that. I want to get rid of all of this stuff here. And I want to process it character by character, right? So I need a character. I'll just call it C, right? Or I can call it current character or something like that. And call fgetC. Right? You pass it the file that you're going to read from. Right? And that gives you a character. Printf. C is equal to %C and the line. Right? So what is the first character in my file? Oh, now it's hello world. How are you? Empty line. I'm good. Thanks. Happy Halloween. Halloween. That looks wrong. It is wrong. There we go. That looks right. There we go. All right. So seven lines here. The first character is a capital H. So when I compile this and I run it, remember that I'm reading it. It's not going to get rid of any data here because I'm just reading from the file. There's the first character, H, right? Capital H. If I did this again, of course I can't have two variables, so I'll just go ahead and do this over and over and over again. So 2 characters, 3 characters, 4, 5, 6. What are the first 6 characters in this file? Hello and then space. Right? Should I continue in this manner? Copy, paste, copy, paste, copy, paste. Probably not, right? First of all, do I know how many characters are in that file up front? Probably not. So let's go ahead and go into some sort of a loop. A for loop or a while loop? I heard while loop out there. Why? What's the justification for a while? I don't know how many characters I'm going to read. If I knew how many characters I'm going to read, right, then I could go into a for loop. So while I'm not at the end of a file yet, the file yet. Right. This is just pseudocode. I'm going to come back and fill it in, right? I'll go ahead and print it out and then get the next character. So now I can get rid of all this stuff, okay? How do I determine if I'm not at the end of the file yet, or if I'm at the end of the file or not? Right? We have a very special character called EOF. So what do you think that stands for? End of file, exactly. While the character that I've read is not the end of file character, go ahead and print whatever you've read out so far, and then give me the next character. There we go. You'll see up here that it starts out, hello world, how are you, blah, 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 all the way down to Halloween. Correctly spelled this time. Right? This EOF character, what is it? Let's look at the ASCII text table and see if we can find it. Look as hard as you can. You will not find it here. It is not a valid ASCII text character. Right? In fact, in C, I believe that it's given a value of -1. We can try to follow it. There we go. There. -1. Do you see that defined anywhere on this table? It starts at 0, hint, right? And goes up. They are non-negative values in the ASCII text values, right? So you will not find this anywhere. Instead, it's a special value that's native to C, right? It's just been defined. Was it defined, right? Was it define macro? Yeah, define end of file to be -1. fgetC returns a -1 value if it's at the end of the file. And that's how you break out of this loop. All right, there. That's basically it. If you want to read a file character by character by character, then that's how you do it. Right? By the way, you could end up with a utility function out of this, right? We said that we don't know how many characters are in a file up to begin with, right? So how could we use this simple loop, put it into a function, and give ourselves that kind of functionality? Maybe some sort of a, I don't know, number of chars in file, right? And we'll go ahead and say const char star file name. Right, there we go. And our return type here will be an integer. We're going to take this entire thing and move it over here to this function. Now, I'm not going to open up myfile.txt all the time. What am I going to open up? Well, whatever file you give me, right, for reading. Now, here is where error handling comes in, right? If, actually, I should have checked if the file name is null, then probably done something there. But if the file failed to open, right, what is a sensible value that I could return? I could return end of file. That would be -1. That would be saying that there are -1 characters in the file that you gave me, right? That's reasonable, right? That's one design. Except that if I can't open up the file that you gave me, I could also always say that I read 0 characters out of it, right? So either way, either design would be fine and perfectly reasonable, right? You just have to document it. Here, I'm just going to return 0, okay? Otherwise, I'll go ahead and keep a counter, int count. I'll start it out at 0. And while you're not at the end of the file, don't print it. Do what? Increment your counter. Close it at the end, and then return the count. Somebody take a look at that and count up the number of characters for me in their head really quick to determine if this is right. Don't worry, I'm not actually going to have you do that. Right? Let's open this up and say int count is equal to number of chars in file myfile.txt. There we go. And print it out. Printf, there are %d characters. And line count. All right. Let's see if it works. There's 60 characters. So how do I know I'm right? 1, 2, 3. Now, what could I do? I could go to an online tool, online character counter. There are plenty of those online. Hey, nice. 60, right? Characters without space, 49. So it is counting the spaces, it's counting the endline characters. I believe it's counting the endline characters, otherwise it would not be correct. Another thing that I could have done is at the command line. There's this utility called WC, which is word count. I can run it on my file, and I can get the number of lines, the number of words, and the number of characters in that file, 60. Right? I could also say LSLA. Right? This is giving me a long form listing of all these files. There's my file. Hey, 60, what does that mean? That means that there are 60 bytes in that file. Right? 1 byte, 1 character. So lots of different ways and utilities that I could check myself and see if this is correct or not. Right? I'm pretty sure it's correct. Okay. Let's go ahead and get rid of that. And I don't know if you want that in your notes, I'll go ahead and put it in there. All right. Demo. C. There you go. All right, so let's look at the other solution, reading line by line using fgets. All right? Fgets or fgets, right? However you want to pronounce it. Right? So the way that this works, fgets gets up to a certain an entire line in the file, right? But limits the number of characters it reads to a certain amount to avoid buffer overflows. overflows. Right? So what do I mean by that? Well, if you've got a string of length, say 100, can you write a string of length 200 to it? If I've only got space to hold 100 characters, can I write something that's twice as big? No. That will overflow that array. Right? That's what we mean by a buffer overflow. Okay. Here is the signature of this function. Right? It takes a string, it takes a size, and it takes a file pointer right here. So what are each one of those? Right? The first argument is the string you want to read the file into. Right? Note there that it does not have a constant in front of it. What should that scream out to you? I'm going to be making changes to this string. Right? It better be big enough to hold whatever you're trying to read, by the way. And that's where the second one comes in. The second argument limits the number of bytes that forgets reads. So you don't overflow the string s. Right? It will read at most size bytes and size minus 1 bytes, and automatically put in the null terminator for you. Excellent. It's doing some of my work for me. This is why it reads in at most size minus 1. Why minus 1? Because it needs room for that null terminating character. The last one should be pretty clear. The third is the file you are reading from. Okay. So let's jump right into it with the same file example over here. File f is equal to open my file.txt for reading. Right? Make sure to close. Usually when I write file IO stuff like this, anytime I say open, I immediately write the code to close and then go back and start filling in the second step of processing the file, just so that you don't forget. Okay. Again, 99 times out of 100, you'll be safe. It's that one time out of 100 that it all blows up in your face and all your data is gone now, right? And there is no undo, there is no undelete, there is no recycle bin, there is no trash bin, right? Those are user-facing stuff, right? And consumer-facing stuff. Right? All right, so let's go ahead and call forgets. Right? I'm going to want to read this into some sort of a string, so I need to create a string. Char, and I'll call it buffer here because that's exactly what it is. I'll make it a size 1000. Now, that is not very robust. For our purposes, though, for demonstration purposes, is any one of these lines more than 1,000 characters? We're not even approaching that. So we'll be able to read in every line here into one at a time. If I had a line with, say, 2,000 characters, right, on that one line, this would fail. Right? It would not read that entire line all at once. Right? I'd have to call it multiple times. So let's go ahead and pass in the buffer. At most 1,000, and I'm reading from the file f. Right? So again, these things have to match. If your string is at most 1,000 characters, then you should be telling fgets to only read at most 1,000 characters. If I did this, I'm risking a buffer overflow. It's going to try to fit as much as it can into that one string, and there's a potential error issue here. Right? Make sure that this matches whatever you're trying to create. Okay? All right, and let's print it out. Printf line is equal to %s and the line, and I'll print out the buffer. There we go. Let's do that a couple of times. 1, 2, 3. Right? Let's read the first 3 lines there. Actually, let's read the first 4 lines. Right? GCC. Run this. Remember the first 4 lines there are hello world, how are you, a blank line, and then I'm good. Hello world, how are you, blank line, and I'm good. I did it 4 times. Why are we getting double space issues here? There's an n-line character in the file right here, 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 and here. And I am printing it right here, 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 and here. So one observation is observation forgets retains the n-line character. if it is read in the buffer. Right? What if you want to get rid of it? You need to cut it out yourself, right? How would you get rid of it? Let's just focus on that first line there. So before we print it, I want to get rid of that end line character, right? Where is it going to be? It's at the end of the line. So how do I get access to the last character, and how do I get rid of it? No? You're doing it right now. Remove char from buffer, the end line character. Hopefully you're doing it right now, right? It's due tonight at midnight. So how would you do that? Yeah, go through, and if you see the end line character, you shift things down, or you create another temporary string, you copy everything over unless it's the end line character, etc., etc. Right? That's one way. What's an even simpler way? Because this is much different from what you're doing in your hack. In your hack, you're removing all instances of, say, a space, or all instances of lowercase o or something, right? Here, this is very specific. There's only one end line character, and it's at the end of the string. What is the index, the last index? N minus 1, and where? How do I get that n? strlen of buffer minus 1. That's going to be the last index in this string. So let's set it. Buffer of that last index is equal to, how do I get rid of it now? Can I set it right back to the end line character? No. To the what? Null terminating character, exactly. Chomping it out. This is known as chomping. Chomping. Removing trailing white space. Not just remove all white space like we did last week, but just remove trailing white space at the end of a string. Right? Now let's go ahead and try that. I only did it the first time, but if I cut and paste, cut and paste, cut and paste, cut and paste, there we go, GCC, run it. Excellent. Hello world, how are you? I'm good. All of those end line characters have been chomped out now. Right? Chomp as in like somebody chews something, right? You're chomping out the characters, you're eating them and throwing them away. Right? Okay. I don't want to do this over and over and over again, just like I didn't want to do this for fgetc. I want to do this until I reach the end of the file. So let's do that. While I've not reached the end of the file, I will do a call to fgets. Right? I'll chomp it out, and then I'll print it. Okay? That means that I can get rid of all this stuff here. So how do we determine if I'm at the end of the file here? I can't use the same trick. EOF is a character. This is not returning a character. This is getting an entire line of characters, a string. So there's also a return value here. Right? fgets also returns a pointer. Usually, this is just a pointer to the string s, or buffer. Right? Unless you are at the end of a file. Right? If you are at the end of a file, what do you think it returns? It's a pointer. What's the only thing that it can return to indicate that I'm done? There's no more left to read from this file. Here's nothing. It returns null, right? The only thing that is representative of nothing with respect to pointers. So over here in my while loop here, I need to capture that value, right? I'll just call it line, char star line, right? Is equal to a call to fgets, while that line is not null. Chomp it out, print it, and read the next line. There we go. Note that I'm doing the next at the end of the loop because this is a while loop, right? You need to set it up so that you're reading the first line, you print the first line. Then you read the second line. And now you're at the top of the function. The second line is valid. It's not null. And you keep going until this returns null. Line is equal to forgets. And then next time you come back up to the top of the while loop, it is null because there is no line to be read, and you break out of it. Let's go ahead and try it. There we go. Uh-oh. Do you see a problem? Mostly it worked. Hello world, how are you? Blank line, I'm good, thanks. Blank line, happy Halloween? Nope, what happened? Why did it cut off that N? Because I was chomping it, right? Is there an end-line character at the last line? No, if there were, it would look like this, and there would be 8 lines. It doesn't look like that. So I'm blindly chomping out the very last character, and if the very last character is not an end-line character, then, right, it's going to chomp that out, that N right there. So let's go back over here and fix it. Remove the trailing white space, but only if it is white space, right? So predicate that on an if statement. If this character that you're in, if the last character is equal to the end-line character, then chomp it out. Otherwise, don't mess with it. All right? GCC this, and I will now get Halloween at the end. Okay? Any questions on this? No? Then let's try to break it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's 100. 1, 2, 3, 4, 5, 6, 7, 8, 9. That's 1,000. And 100 more. Right. So I don't have a character counter here for the line numbers here, but this first line is now more than 1,000 characters. Right? How is this going to be treated now? It's not going to result in a segmentation fault. It's just going to result in something else. Here's that first line. It read the first 999 characters. I can guarantee you that that's 999 characters there. Why? Because the null terminating character. It needed room to put that null terminating character in the, at the end. Otherwise, it would not have been a valid string. Right? So it read the first 999 characters, and then the remaining characters it read on the next time you called it. So if you have very long lines, say, and lots of data is like this, DNA data that you'll be dealing with in your hack this week. If you have very long lines, lots of times people will just cut those off, right? And limit line numbers to say 70, at most 72 characters. And so even if there is very long data like this, it'll chop it up into smaller lines or shorter line chunks. In which case you need to go back and remove all that white space if you're going to treat it like one big giant piece of data. Right? Or you need to make sure that your program, when you're processing that data, that you know that you did not get to the end of the first line. Instead, why? How do you know that? Because you don't have the end line character here, right? But the next call got you the rest of the line right here. All right? And then the rest of it. Hello, how are you? I'm good, thanks. Happy Halloween. All right? Okay. Let me make sure that you've got this at least. Here it is, line by line, using fgetS instead. See. There you go. Oops, there we go. All right. That's good, that's good. No questions so far? No? All right. Got plenty of... I've got only 5 minutes. We'll probably continue this next time. Here, let me set you up for an experiment that you'll do in your lab tomorrow, right? So let's talk about binary data. Like I said, our focus is going to be not on binary data because you should be pulling in a library to do it for you. But we should understand the difference between binary data and text data. So how many bytes does it take to represent the largest value, largest integer value? Say, what is that going to be? Wolfram alpha 2 to the 31st, which is 2.147 billion minus 1, sorry. There we go. There, that number right there. That's the maximum value that you can represent as an integer, right? So this value, right? In text, using plain text, right? Using binary. Right? So you tell me, how many bytes does it take to represent 2147483 If I put that into a string as plain text, like this, right, how many bytes are in there? Remember that each character is 1 byte. And those numbers are not numbers, they are characters in the ASCII text values, the text table, right? ASCII text values 48 through 57 represent numbers. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? This is at least 10 bytes, okay? But if I represented it in binary, do I need nearly that many bytes? Size of int is all I need. This is typically what? Usually what? Only 4 bytes, right? So which one is better? Well, it's only 6 bytes, who cares, right? Well, you care when you're storing massive amounts of data, right? When you're storing, say, 50 million integers, or the equivalent of 50 million integers. Are you going to want to store that all as plain text, which is going to be more than 2.5 times as big? Or are you going to want to store that as pure binary, where it's going to be, you know, less than, what is it, like 40% of, or 40% of the original size, right? Now you start to see the massive difference between these two. If it is not meant for human consumption, you probably want to store it as binary. If I stored 10 of these integers, it would be a huge difference. It'd be the difference between 100 bytes and 40 bytes. That's 60 bytes. If I did it for 10 million, right? Now you're talking about the difference between megabytes, right? Billions, trillions, now you're talking about a difference in terabytes of storage. Right? So the takeaway here is that using binary is probably way more compact. In your, I'll show this next time after you had a chance to do it in your lab, but in your lab we've already set up the experiment for you. What it does is it creates these numbers, dumps them to a binary file, dumps them to a plain text file, and then you have to look and see the relative size of those two things. Right? And that's what you'll do tomorrow, and then we'll pick it up there on Wednesday. Otherwise, I don't know, happy Halloween. Right? Trick or treat, whatever.